Okay, so we are going to talk sum and difference formulas. Sometimes they're referred to as the sum and different, I can't speak, sum and difference identities, but they mean the same thing. So we have sum and difference formulas for sine, cosine, and tangent, and I've included them right here. Now, this is something that I don't expect you to memorize, so we will provide a formula sheet for tests moving forward. So for test 2 and the final exam, so you'll have access to these, and we're going to add them as we move through the course. So let's talk about how to apply these. So what these enable us to do is to find exact values for functions of angles that aren't those 30, 60, 90, 45, or angles who have a 30, 45 degrees, 60 degree reference angle. So for example, let's say we were looking to find the exact value of cosine of 195 degrees. So if you think about it, right, at this point, what we would normally do when it says find the exact value is we would think about, okay, well, where would 195 be on our xy plane? And so since we know this is 180 degrees, this is 270, so it would be somewhere here in quadrant 3, right? And the reference angle would be 15 degrees. So that's not one of those special triangles that we know those exact values of. So that's what these formulas allow us to do, is we can break 195 degrees up into the sum or difference of angles for which we can find exact values for. So what I'd like to think about is, I think sometimes the hardest part is figuring out how I want to break up 195 degrees. Because we want to break up 195 degrees using angles that we already know. So using the 30, 45, 60, 90, and anything that would have a reference angle of those to come up with 195. So since we have a 5 here, I'm thinking that 45 is going to be part of this. So what I tend to do is like, okay, let's just subtract 45 from 195 and see what we get. So when I subtract 45, we get 150. And 150 has a reference angle of 30 degrees, so I can find an exact value of 45. I can find an exact value of 150. So I can think of 195 degrees as 150 degrees plus 45 degrees. So that's what we're going to do. So we're going to think of this as cosine of 150 plus 45. And we're going to apply, since we're adding, this identity. So in this case, we are using our A is 150 and our B is 45. So if you think about this formula, so let's write down the right side of the formula. So this, we're going to use cosine A, cosine B, and then we're subtracting sine A, sine B. So now let's make those substitutions for our A's and our B's. So this will be cosine, we're saying A is 150 degrees, times cosine B is 45 degrees, minus sine of 150 degrees, and then sine times sine of 45 degrees. Okay, so we can find the exact values of these. So let's think about this. So let's start with cosine of 150. So I'm going to go ahead and draw that triangle, right? So again, if this is 180, 150 would be here in quadrant 2. And so that's where I'm going to draw my triangle. And the difference between 180 and 150 is 30 degrees, so that tells me my reference angle. And then I know opposite 30 is 1, the hypotenuse is 2, and then adjacent is the square root of 3. I'll also want to keep what's positive where in mind, and that's where I kind of think about that CAST. So things I want to know here is cosine of 150. So I'm looking at this triangle, cosine is adjacent over hypotenuse, and cosine is negative in quadrant 2. So cosine of 150 is negative square root of 3 over 2. To that, I'm going to multiply cosine of 45 degrees. So again, that's our 45, 45, 90 triangle. We could draw that also in quadrant 1, although I'm thinking by now we probably have that memorized. So cosine of 45 is square root of 2 over 2. Sine of 150, so sine is positive in quadrant 2, so that's 1/2. And then sine of 45, again, is square root of 2 over 2. And that comes from that 45, 45, 90. Okay, so remember, we multiply before we subtract. So multiplying a negative times a positive, so square root 3 times square root 2, we multiply what's on the inside. So that's square root 6, and it's negative. 2 times 2, multiplying those denominators is 4. And then minus 1 times square root of 2 is square root of 2, and 2 times 2 is 4. So if I could simplify a little bit more, I would, but this is good. You could also write this with one denominator since the denominator is the same. Square root of 6 minus square root of 2 over 4. But I believe either would be acceptable. So let's try another one. All right, so let's find the exact value. Why don't we work in radians so we can practice that. Let's find the exact value of cosine, or let's change functions too. Let's do sine of 5 pi over 12. Okay, so same thing. If we're thinking about this, how we have in the previous sections, we would be thinking about, okay, where would 5 pi over 12 be on the unit circle or on our xy plane? And so since we have that denominator of 12, we can think of pi is 12 pi over 12. Pi over 2 would be 6 pi over 12. So 5 pi over 12 would be somewhere, right here. Remember that reference angle is always made with the x-axis. So that would give us a reference angle of 12 minus 5 is 7 pi over 12. And again, that's not one of our special angles from our special triangles, right? Those special reference angles that we think about are pi over 3, pi over 4, pi over 6, and any of those quadrantal angles like pi over 2. Those are the numbers that we can work with. So that's what indicates, okay, I'm going to have to use some kind of identity to find an exact value. And that's where these come into play. So can I rewrite 5 pi over 12 as the sum or difference of angles for which I can find exact values? So it's just like before, where I would start with is subtracting one of these angles from 5 pi over 12 to see what results. So if I'm looking at this, so 5 pi over 12, we could really grab any of these. I'm going to grab pi over 6. So if I subtract pi over 6, what results? I would need a common denominator, so I'd have to multiply by 2, top and bottom, right? So this would be 5 pi over 12 minus 2 pi over 12. 5 minus 2 is 3, so 3 pi over 12 would be the difference. So 3 pi over 12 would reduce, I can reduce by a factor of 3 to pi over 4. So this would imply, right, when I subtract pi over 6 from 5 pi over 12, I get pi over 4. So we can say that 5 pi over 12 is equal to pi over 6 plus pi over 4. So that's what we'll break that up that way, and we'll apply the appropriate formula. So we can say, okay, this is the same as, and again, this isn't the only way we could have broken it down. You could have chosen 2 different angles that also add together to 5 pi over 12. The math will still work out the same way. There's not one way to break down these angles. There's multiple possibilities, all of which will lead to the same place. I picked pi over 6 just because it was easy to convert it to a denominator of 12, but really 3 and 4 would have been easy as well. So I'm going to rewrite this as pi over 6 plus pi over 4. So again, remember, those, if you have those converted with denominators of 12, it's a little easier to see how they add to 5 pi over 12. Okay, so now let's think about, we're going to call this one A and this one B, and then we're going to apply, since we're adding, we would be using this identity. So this is, I'm going to jot that down. So jotting down the right side, sine A cosine B plus cosine A sine B. Okay, so let's fill in the appropriate things. So this would be sine of pi over 6 times cosine of pi over 4 plus cosine of pi over 6 and sine of pi over 4. Okay, so these are all of those special triangles, right? Pi over 6 is the same as 30 degrees. So again, opposite 30 is 1, hypotenuse 2, square root of 3. So that's our pi over 6. And again, like we talked about before, that 45, 45, 90 is 1, 1, square root 2. So sine of pi over 6, or 30 degrees, is 1/2. Multiplying to cosine of pi over 4, which is square root of 2 over 2. And then adding to that, cosine of pi over 6 is square root of 3 over 2. And sine of pi over 4 is square root of 2 over 2. So now multiplying numerators, multiplying denominators, I end up with the square root of 2 over 4 plus the square root of 6 over 4. Okay, let's do one more. Let's do a tangent one just so you have a nice example of each, and then we'll pause. So let's finish with tangent of 15 degrees. Okay, so immediately what comes to mind for me when I'm thinking about those special angles is the subtraction of 45 minus 30. So that's what I'm going to do. Let's say, okay, this is the same as tangent of 45 degrees minus 30 degrees. And then we'll apply the appropriate since we're subtracting, we would be using this one. So I'm going to jot that down. So that's tangent A minus, make sure, tangent B. And then that all gets divided by 1 plus tangent A, tangent B. Okay, so again, this is our A, this is our B. Let's plug in. So this is tan of 45 minus tangent of 30. And then this gets divided by 1 plus the product of tangent 45, tangent 30. Okay, so tangent 45, opposite over hypotenuse, so 1 over 1 is 1, minus tangent of 30, jumping over to this triangle, so opposite over adjacent is 1 over square root of 3, or I'm just going to go ahead and write that as square root of 3 over 3. And then on the bottom we have 1 plus, and then again tan of 45 is 1, and tan of 30 is square root of 3 over 3. So let's think about the arithmetic here. I want to think of 1 also as a fraction, so I can rewrite that as 3 over 3. So 3 minus root 3 is my numerator, 3 is my common denominator, and then this is over, so let's see, this is going to be 1 plus root 3 over 3. So similarly, thinking of 1 as a fraction and multiplying by 3 over 3, in that denominator I'll have 3 plus root 3 over 3. I'll jot down that numerator again. Sometimes this is the more difficult part, is simplifying with the arithmetic. So remember, when I'm dividing fractions, this is 3 minus root 3 over 3. You change division to multiplication of the reciprocal. So this is 3 over 3 plus root 3. Those 3's cancel on the diagonal. And my final answer is the numerator of 3 minus root 3 over a denominator of 3 plus root 3. In some trig classes that you may or may not have taken in the past, sometimes you have to rationalize the denominator. You do not in this case. This is considered simplified enough in terms of ALEKS.